All right, so today is the next lecture on module 4, which is called excess carriers. So this time in class, our main goal in today's class is to talk about diffusion, which is a type of, one way that carriers can move. So just for a little bit of context, last time in class, we talked about how you can create carriers by light. So we talked about carrier generation processes. Last module, we talked about how you can generate carriers with changes in temperature and doping. This module was about how you can create carriers by shining light on the material. And then we got into the movement of carriers. Last module, we talked about how carriers can move under an electric field that is called drift current. And today we are going to talk about how carriers can move due to diffusion. So, and we also talked about recombination last time in class, direct and indirect. So at the end of this module, we want to have a good understanding of all 4 of these carrier processes: carrier generation, which is the carrier creation of a carrier due to heat, light. So this depends on doping. While after a carrier is generated, so an electron or a hole can move due to electric field, which is drift. It can move due to concentration gradients, which we talk about today. That is called diffusion. And then after some period of time, the electron or hole disappears, or it becomes annihilated. That's what we talked about in class last time, recombination. So I just want to remind everyone that this is something that depends on carrier concentration. Recombination is when an electron and hole, they meet each other, and the electron occupies the empty state, and both the electron and hole are annihilated simultaneously. So this process is due to electrons and holes. If they're near each other, the more electrons and holes you have, the more likely they'll be near each other, the more likely they will be to bump into each other. And so that's why it depends on carrier concentration. And the last point I want to make here is the carrier lifetime. The time between generation and recombination processes can be on the order of picoseconds, nanoseconds, microseconds. It's a very short amount of time is the main thing that I want to put out there. All right, so what we have to do is we really have to think about these processes happening continuously. Carriers are always being generated, they're always recombining. And while that short time period that they happen to exist, they can either drift or diffuse or both. So all 4 of these processes, this is going to be the second thing we talk about today, is we're going to talk about the continuity equation. So we have these 4 processes, and we'd like to have one equation that describes all of it. Okay, the unifying equation. So once we get through talking about diffusion, then we'll get into the continuity equation. We'll give you the overall equation, and then we'll go into some very specific examples of the continuity equation in specific cases. For example, steady state injection. All right. So our main focus is diffusion, but we're also going to end up talking more about carrier generation. We'll talk about steady state generations, transient generations. So let's get right into that right now, because that is important in talking about things like diffusion. Okay, so let's take a step back and let's look at all the different types of stimuli in electronics. What we're going to do today, let's talk about the different types of stimulus. Okay, in engineering systems, we often apply a stimulus to a system and then we measure the response. So there are some, in mechanical engineering, we apply a stress to it and we look at the strain. In chemical engineering, we apply a constant, we can apply a chemical and then we look at the chemical reaction. We look at the response of the chemical reaction, things like that. So in electronics, the types of stimuli we often apply an electric field. We talked about that, a few classes ago. A drift current is a result of an electric field. Last time in class, we also talked about light. Okay, if we want to generate carriers in an electronic material, we can shine light on it. We could also apply heat, which generates electron hole pairs as well. So why are we talking about this? Well, when we start getting into talking about diffusion today, diffusion turns out to be like the movement of carriers from high to low concentration. So then the question becomes, how do we create that concentration gradient? And it turns out light is a good way to create that concentration gradient. So there are different ways that light can be applied. We can talk about steady state light. We can talk about transient light. So it's worth talking about what these different states are. So let's start with the basic one. An equilibrium situation. So we talked about last time in class, equilibrium, what does carrier generation and recombination look like at equilibrium? We said that they're equal to each other, right? In an equilibrium situation, the definition of equilibrium is that there's no external excitation. So there's no light applied, there's no electric field applied, there's no heat applied to the system. Like room temperature is not considered an application of stimuli. So just keep that in mind. So if we're not applying any kind of excitation and we're at constant temperature, we'll be in an equilibrium state. In an equilibrium state, there's no net current and carrier concentrations do not change with time. Carrier concentrations means the electron and hole concentration, they don't change with time. Okay. So equilibrium would be this first part of this first column in the table. The type of stimulus, there's no stimulus. Carrier concentrations don't change with time. And the currents in the system, there's a net zero current. This is going to become important when we talk about diodes. Okay. Equilibrium is the most specialized case. If you like thinking about things in terms of Venn diagrams, equilibrium is the most specialized case where the stimulus is basically zero. Now, the next circle in the Venn diagram is steady state. This is where you have a stimulus, but it's constant in time. So steady state, when we talk about analysis of electrical circuits, we talk about the steady state voltage, the steady state current. For all the chemical engineers, when in chemical engineering, when we're talking about steady state, we look at steady state concentrations. Sometimes at the beginning reaction rates are, changing, but then you get to a steady state where the product and reactant concentrations are fixed. So steady state means you are applying an external excitation. So let's say, concrete example, in a semiconductor, we are applying light to the system, but that light is not changing with time. It's a fixed light source. It's constant in time. That would be an example of a steady state stimulus. Another example would be if we were applying a voltage to the semiconductor, and that voltage is constant in time. That is also an example of steady state. Processes are constant, and they are processes are happening, but they are balanced by opposing processes. For example, in the case where we're shining light on the semiconductor material, in steady state, the generation is balanced by recombination. So the generation rate and recombination rate, along with drift and diffusion, they all end up balancing each other out. Okay, this will make more sense when we talk about the continuity equation. Main point here, steady state, the type of stimulus is constant. The carrier concentrations do not change with time in a steady state situation. And the currents are constant. The currents do not change with time. Okay, that's the difference between equilibrium, is that equilibrium has zero net current, steady state has a constant current. The final situation, the most general case, the largest circle on the Venn diagram is the transient situation. This is where you have a stimulus, but that stimulus can change with time. So an example, an example in mechanical engineering is where you are applying a vibration to a system, or you're just hitting a material with a hammer, and it's causing a time varying shift in the stress and strain. In electronics, or electrical engineering, stimulus, we can think about electric fields and light. So imagine that we apply an electric field or applying a voltage that changes with time. Like we often talk about the step response of an electrical circuit, where the voltage goes from 0 to 5 volts, and we look at how the circuit responds over time. What we're going to be talking about today is transient light. So let's say we shine light on the material, we just turn the light on. How does the semiconductor change? Then when we suddenly turn the light off, how does how does the carrier concentrations change? So we'll talk about that. In the transient situation, the currents and carrier concentrations can change with time. So this is the most general case, and being the most general case, it's often the most complex case as well. Okay, so we're going to be talking about steady state excitation with light. We're going to be talking about transient excitation with light in a semiconductor today. Okay, but just remember these three concepts of equilibrium, steady state, and transient. This applies to all areas of engineering. Okay. Just a soapbox point here. I think being a good engineer, a fun thing about being an engineer is knowing that these same engineering principles actually apply throughout different engineering fields. My research that I've done over the past however long I've been in this field is that I work in a very interdisciplinary field. So I look at aspects of mechanical engineering, chemical engineering, electrical engineering, and I find there's a lot of similarities between the disciplines, a lot of similarities, this being one of them. So I want to impress that upon you as much as possible. Okay. So let's look at steady state carrier concentration first. Okay, so this is where we have a semiconductor material. And what we're going to do here is we are going to illuminate it with light. Okay, so let me just advance the slide here. There we go. So imagine that we just illuminated the entire semiconductor material with light. So when we turn the light on, of course, we're going to generate electron hole pairs, but we're going to leave that light on. We'll leave it on so it achieves steady state. Okay. So you all see what's happening here. When you turn on the light, you generate electron hole pairs, just like we talked about in class. Okay. And depending on how intense, how much, depending on the optical power that's applied, depending on the optical power, you'll generate more or less electron hole pairs. So if I increase the optical power of the light, you'll increase the number of excess carriers. Now, these are called excess carriers. Let me define what that is. Before we shine light on the semiconductor material, the semiconductor might be N-type, it might be P-type, it might be intrinsic. It already has a electron and hole concentration. So non-illuminated we can say that the semiconductor material has a concentration N0, electron concentration N0, and a hole concentration P0. When we turn on the light, oh, by the way, N0 and P0, I haven't drawn those. I haven't drawn the electrons and holes in the material, okay? But when I illuminate the material, now I generate additional electron hole pairs. So we can say in the illuminated semiconductor, we generate, we can say that there's an excess set of carriers. So now the electron concentration N is going to be equal to N0, which was the initial amount when it was non-illuminated, plus delta N. Okay, that delta N is the excess electron concentration. Similarly, the hole concentration is going to be the non-illuminated hole concentration plus the excess hole concentration that was generated by the light. Okay, and notice the excess carriers are generated in pairs. So, sigma n is going to be equal to sigma p. So they are generated in pairs together. Let me actually, we have to be careful about saying sigma n is equal to sigma p. I'm going to just erase this so it doesn't create confusion in the notes later, because the steady state excess concentrations can actually be different depending on the carrier lifetime. So I'll get into that just now in this slide. Okay, so everyone can hopefully see that you're generating excess carriers here. Now, I'm just going to give you a formula. If the light source happens to be fixed in time, if it's steady state, then this equation here gives the steady state excess carrier concentration. Okay, so this sigma n, okay, the sigma n that we're talking about here, here's the formula for the sigma n. Okay, it says sigma n 0 here, but it's the same as the sigma n, okay? So this sigma n is equal to tau sub n times GOP. Okay, let's look at what those individual components are. GOP describes the number of carriers created per second. So this GOP has to do with the light source here. Okay, as I said, the more intense the light source, the more carriers are going to be created per second. All right. More carriers are going to be created per second. So a typical number might be 10 to the 15th electron hole pairs per centimeter cubed per second. If we shine some kind of light on silicon. If we increase the intensity of the light source, maybe that can go up to 10 to the 20th or even more. The second component here, tau sub n, is the carrier lifetime. Carrier lifetime. The carrier lifetime has to do with, as I mentioned, it's one of the 4 carrier processes. Okay, the carrier lifetime is the time between generation and recombination events. How long a carrier lives before it recombines. Okay, so the units for this is seconds. And a typical value might be, 10 nanoseconds, could be in microseconds. It could even be in picoseconds, depending on what type of semiconductor you have. The product of these two gives the steady state concentration in electron hole pairs per centimeter cubed. And so if we just remind ourselves what the units are, electron hole pairs per centimeter cubed per second. That's the units for GOP. The units for tau sub n, the carrier lifetime, is in seconds. Okay, so if you multiply seconds by electron hole pairs per centimeter cubed per second, then you'll end up getting a unit of electron hole pairs per centimeter cubed. Okay, sometimes this is just, you don't even say electron hole pairs per centimeter cubed, you just say 1 over centimeter cubed is the units. Okay, depending on who is teaching you, a lot of times this is used 1 over centimeter cubed. Okay, so this gives a steady state concentration, and I want you to see the intuition behind this. Okay, GOP we already talked about. If you increase the intensity of the light source, then of course you're going to have more excess carrier concentrations because you're just generating more electron hole pairs. The second part here, the carrier lifetime, if the carriers that you generate live for a long time, then of course your excess carrier concentration is going to go up. On the other hand, if the lifetime is very short, that means the light source is generating these electron hole pairs, but they're quickly recombining. In that case, well, then you're going to have a lower excess carrier concentration. Okay, this is a very simple formula, but I just want you to recognize the intuition of these formulas. Okay, similarly for holes, there's a similar equation for holes. Sigma p is equal to the carrier lifetime for holes times GOP. Okay, and this brings me to the point I mentioned earlier. If tau n and tau p are the same, if they happen to be equal to each other, then sigma n and sigma p are also going to be the same. But sometimes the electron and hole carrier lifetimes may end up being different. Okay, so we can't necessarily assume that they're going to be the same in all situations. Okay, so we're going to do an example problem here. Assume we are shining a laser light on an N-type silicon wafer so that in the irradiated area, 10 to the 13th electron hole pairs per centimeter cubed are created every microsecond. Okay. Note here that I'm giving you GOP, but I'm giving it to you in a different units. I'm giving it in units of microseconds. So you just have to be, you may need to do a unit conversion there. Okay. Assume the SI doping is NO is equal to 10 to the 14th per centimeter cubed. In this case, the electron and hole carrier lifetime are the same, 2 microseconds. So what I'd like you to do is calculate the equilibrium concentration of electrons and holes. Equilibrium means before we shine light on the material. And then I want you to calculate the excess electron and hole concentration created after irradiation. So asking you to calculate sigma n and sigma p. And then I'm going to ask you to calculate the total concentration. Okay, so this is asking you to calculate N0 and P0. This last part is asking you to calculate N and P, which is the total electron and hole concentration. Okay, then this last part is I want you to just compare. How much did the hole concentration change? How much did the electron concentration change before and after irradiation? All right. So this is important problem, not terribly difficult math-wise, but I'd like you all to just try it for the next 4 minutes or so, 4 or 5 minutes. Okay, I will mute myself, and if you have questions, just go ahead and blurt them out. And if you, I'm just going to, for simplicity's sake, I will just put the equations here. Just as a reminder from the last slide. Okay. All right. So go ahead. I'll give you a few minutes to do that. Give it a shot. Okay. So I'm curious if anyone was able to calculate the. I'll show the solutions on the next slide, but I want to see if see what folks got before we do that.
I guess the equilibrium would be in the absence of this irradiation. So we have N0, of course, 10 to the 14th, and then we have P0 using NP equals NI squared
Yep.
to be 2.25 times 10 to the 6th, I believe.
Mm-hmm. Sounds about right.
The excess holes and electrons created by the radiation had to do a unit conversion, I think, like you mentioned, to convert it from microseconds to seconds. So you end up with, what is that? 10 to the 19th electron hole pairs per centimeter cube per second. And then, yeah, then you just, you pretty much just add those up to each other. They're both the same. So we can say that the carrier lifetime is the same. So we can just say that, just add both of those together, and then the percentage would just be, the division between the two.
Very good. Very good. Yeah. Great. Yeah, that's so Melvin's right on. The processes that you talked about are pretty much what I'm going to show here. So let's just go over before irradiation and after irradiation. So everyone just check over your work here to see if yours matches up. So as Melvin said, before irradiation, and this is stuff you've done in module 3, calculating the electron and hole concentrations, your doping is given to you as 10 to the 14th per centimeter cube. So we assume that all the dopants are create 1 electron each. So N0 is equal to 10 to the 14th per centimeter cubed. I don't have the units here. I would like to make sure that you do put your units on your, when you do exams and homeworks and such. P0 can be found with NP equals NI squared. Okay, so P is equal to NI squared over N0. And that comes out to 2.25 times 10 to the 6th. Again, the units for these is going to be per centimeter cubed. Okay, typical N-type semiconductor, your electron concentration is many, many orders of magnitude above your hole concentration. After irradiation, so these are the calculations that we do here. We first calculate the excess carriers. Sigma n is equal to tau n times GOP. So what we did here is the tau n is 10 to the 13 divided by 10 to the negative 6. So this is that unit conversion that Melvin was talking about. If you want to convert electron hole pairs per second, per microsecond into electron hole pairs per second, then you would just divide by 10 to the negative 6. And then GOP is given to us as 2 times 10 to the negative 6 seconds. That's why we have the 2 times 10 to the negative 6 here. And so the sigma n, the excess electron concentration, comes out to 2 times 10 to the 13th per centimeter cubed. And since tau n and tau p were the same, if you plugged in if you did the same approach for the holes, you'd find that the excess hole concentration is also 2 times 10 to the 13th per centimeter cubed. All right, so fairly straightforward. And then the total carriers, to find the total electron concentration, we have to add up the initial concentrations. That's what we calculated here before irradiation. So this is the initial amount, and then we add the excess electron concentration. So it's 10 to the 14th, what we had here. Add the excess, which we calculated here, 2 times 10 to the 13th. Then we get 1.2 times 10 to the 14th. Again, the units are per centimeter cubed. And then doing the same formula for the holes, there's one thing that we notice here. Okay. So same formula, P is equal to P0 plus sigma P. P0 is 2.25 times 10 to the 6th before irradiation. And then sigma P is 2 times 10 to the 13th. That's the excess carrier concentration after irradiation. Now, in this case, one of the things we notice here is that P0 is 2.25 times 10 to the 6th. Sigma P is 2 times 10 to the 13th. Many orders of magnitude above P0. So that's why in this case, we can basically say this is approximately equal to sigma P. This sigma P is much larger than the P0. This is equal to 2 times 10 to the 13th. Okay. So when we look at the percentage change, we look at how much, after shining light on the material, by what percentage did the electron concentration increase? The electron concentration was originally 10 to the 14th. After irradiating it, it went up to 1.2 times 10 to the 14th. Okay, 10 to the 14th to 1.2 times 10 to the 14th. That is an increase of 20%. Okay, so it increased, yes, but fractionally, percentage-wise, it didn't change all that much. The whole concentration, on the other hand, it was previously 10 to the 6th, and now it's 10 to the 13th. So the number of holes, we can say that it increased by 2 times 10 to the 13th divided by 2.25 times 10 to the 6th. That's about 10 to the power of 7. If you divide this by this. So fractional change in the number of holes, it went up by 10 to the 9th percent. That's a huge fractional change. The absolute change was the same, identical, 2 times 10 to the 13th. That's the increase in electron and increase in hole concentration. But the fractional change was very significant for the holes. So this is this type of situation where one carrier concentration fractionally didn't change very much, but this is called the majority carrier. The electron in an N-type semiconductor, the majority carrier is the electron because you have a lot of electrons and very few holes. The majority carrier is the electron. The minority carrier is the hole in an N-type semiconductor. You can see the majority carrier concentration, it only changed by 20%. Minority carrier concentration changed by a lot. So these are the types of situations that we refer to it as a special name. This is called minority carrier injection or minority injection. Okay, this is where majority carrier concentration changes not much. The minority carrier concentration changes a lot. Okay, I'm giving you a colloquial definition, right? Majority injection is where, both the electron and hole concentration changes significantly.
So, sorry. So the majority injection would correspond to, I guess, the more general case where the tau N and tau P, the lifetime of the carriers, are not the same. Whereas this specialized condition where tau N, tau P, when they're the same, then we can say that there is going to be a minority injection. Would that be
not quite. It's really based on the percentage increase of the electrons or holes. So you can see that in this case, the percentage increase of the holes, which is the minority carrier in this case, it changed very significantly, but the majority carrier concentration only changed by 20%.
I see. I see.
So if let's say, let's take an example where the GOP, instead of 10 to the 13th, let's say it was 10 to the 14th, or let's say it was 10 to the 15th. Okay, let's say it was 10 to the 15th. All of the excess carrier concentrations are going to go up by 2 orders of magnitude. So this will become 2 times 10 to the 15th. This is 2 times 10 to the 15th. And then what would end up happening is that the percentage change in your electrons is the electron concentration would go up by a factor of 100 instead of just a factor of 20%. So in this case, both of the electron and hole concentration changes significantly.
I see. All right. Thank you.
That makes sense? Okay, great. Okay, good. So let's move on then. Any other questions on the carrier generation and recombination? Okay. All right, so let's move on to the concept of quasi-Fermi levels. So the quasi-Fermi levels are a way for us to understand excess carrier concentrations in the language of energy band diagrams. So one of the themes, obviously, you're seeing in this class is that we like to explain things in terms of the physical model. We like to think about electrons and holes physically in the material, moving around, being generated, recombining, and so on. But the energy band model is where we draw the EC, EV, and so on. So when we create excess carriers with light, physically what we're thinking is, oh, okay, the light is so in the physical model, we think about this: that light hits the semiconductor and it generates this electron hole pair. In the energy band model, we think about this: the light hits the semiconductor and the electron goes up into the conduction band, and then it creates an electron hole pair. Now, we just want to expand on this energy band model a little bit by putting in something called a quasi-Fermi level, which indicates these additional electrons and holes that are formed. So let's go back to the slide we were on. Here we go. Okay, so let's talk about this conceptually. So first of all, when we generate carriers in a material, both the electron and hole concentration changes, okay, because they're formed in pairs. We know that already. So one way that we can represent this is by a quasi-Fermi level, and this only applies to steady state analysis. It does not apply to the equilibrium analysis. It does not apply to transient analysis. For equilibrium analysis, we have our usual Fermi level, E sub F. Okay, this quasi-Fermi level I'll show you is used for steady state. Okay, so I'll explain what it is first, and then hopefully we'll have understand the intuition behind it a little bit. Okay, this is the equation which describes the electron and hole concentrations in terms of a quasi-Fermi level. Okay, you'll notice that this is very similar to the original equation for electron concentration. You have your n sub I, and then you have the exponential of the difference in two energies. So just to remind everyone, I'm just going to put the original equation up here. So if you're not irradiating the material, the electron concentration n sub 0 is equal to Ni e to the E sub F minus E sub I over KT. Okay, and there's a similar equation for the holes. So what you see here, if you compare these two equations, the Ni is the same, that you still have an exponential. Basically everything's the same, except instead of EF, instead of E sub F, you have this F sub n, which is the quasi-Fermi level for electrons. So let's see what that looks like. So you have your conduction band and your valence band lines, same as before. You have your intrinsic level, the same as before. Now let's just assume that we have an N-type semiconductor. So we're assuming N-type in this example. And now we're going to add F sub n and then F sub p. Okay. Now, one of the things you'll notice is that F sub n and F sub p, they're going to be similar distances to E sub I. So they're almost going to be mirror images of each other, because the excess electron concentration and the excess hole concentration are usually, often the same. The exception I mentioned before is if they have different carrier lifetimes. Okay, so we introduced two additional lines in the energy band diagram, F sub n and F sub p. And the way that I like to think about it, the way I like to visualize it, is that the higher F sub n goes, higher F sub n, that means more sigma n, more excess electrons were generated. So the way I'd move this F sub n up is I would just increase the intensity of the light. So that would create more excess electrons. So, and vice versa is also true. If we want to move F sub n down towards E sub I, then we'd want a lower sigma n. So lower F sub n, this indicates lower excess electrons. Now the lowest F sub n can go is to EI. Okay, because when F sub n is equal to EI, this whole exponential just becomes exponential of 0. And so then the electron concentration becomes Ni. Okay, and the same thing for F sub p. The closer F sub p, the lower it goes. In the case of F sub p, the lower it goes, farther away from E sub I. That means you get more hole concentration. So I'll just put this down here. Lower F sub p indicates more excess hole concentration, more sigma p, and then vice versa. Okay. So really these lines are just a way to visualize the excess carriers that you've generated. So this example that I've drawn here is the case that we discussed in the example problem that we just all did as a class together. This was a case of minority carrier injection. So you can see that the F sub n is below E sub F. Okay. So hopefully everyone has an intuition of what E sub F is right now. What does it mean when E sub F is above EI? What does that tell us?
There's a probability of more electrons towards a conduction band.
Exactly. So what type of semiconductor is it?
That would be an N-type.
N-type, right. And what happens if we dope? Well, what happens to the Fermi level if our electron concentration goes up? If we dope the material more N-type, what happens to the Fermi level?
It shifts upwards.
It shifts upwards towards E sub C. That's right. That's right. So basically like that intuition. I look at the energy band diagram and I see where E sub F is. And in my mind, I'm thinking, well, the higher E sub F is, the higher the Fermi level, the more N-type the material is. Similarly, with F sub N, depending on where that quasi-Fermi level is, in my mind, I'm thinking, well, how many extra electrons did I add into this material by shining light on it? And if I see that F sub N is below E sub F, that means, well, I haven't really changed the electron concentration by all that much. If F sub N goes above EF, like for example, if F sub N was way up here, then I would know that, well, I've changed the electron concentration quite a bit. On the other hand, let's look at the other side of things. E sub F, it tells us not only about the electron concentration, it also tells us about the hole concentration. The fact that E sub F is above EI here and it's closer to EC, that tells us, well, there's a lot of electrons and there's very few holes. When we draw in this extra quasi-Fermi level with the holes, F sub P, and this F sub P is actually below EI, and it's closer to EV, this is, in a way, it's telling us, this diagram is telling us that, wow, that our hole concentration changed quite significantly. So this material is, quote unquote, like, it could behave more, it has hole concentrations that are closer to a P-type material now, because we've all these extra holes that we put into there by shining light on the material. Okay. So all I really need you to be able to do in these quasi-Fermi level problems is just to be able to draw the energy band diagram showing the original Fermi level before irradiation and then the new quasi-Fermi levels after irradiation. Okay. So in the interest of time, we're not going to do this in class. I just want you to use these equations to figure out and draw the locations of the quasi-Fermi levels, very similar to how you draw E sub F. Okay. So we'll do that. I would like you to just do those problems on your own as homework.
Hey, Professor.
Yes, go ahead.
I don't have a question more so about this topic, I guess, about just the examples in general. I know a lot of the examples we don't have the answers in the lecture slides.
Yes.
Is it possible that we could get those, so just so that when we're kind of going through them, we can kind of know what the right answer is? Just
sure. Yeah. In fact, why don't I just, you all have access to the recording here, so
perfect.
I'll just flash this up here for just for now, okay. And you can find that section of the video. And this section here, I know this is in my terrible handwriting, but this is where I calculate the location of F sub N, and this is where I calculate the location of F sub P. Okay, so go through these on your own and see if your answers match up with the ones that I've shown here.
Thank you.
Okay, so moving on. Now we're going to talk about transient stimuli. Okay, so we're going to the more general case where we're applying a stimulus, we're applying an optical stimulus, but now that optical stimulus is changing in time. Okay, so let's see what that looks like. Again, I'll have like a kind of a graphic to get this point across here. So carrier lifetime can be understood in a simple example, where we just illuminate a material with light. Okay, so same as before, we're illuminating with light. We, of course, generate the excess electron hole pairs just like before. And we just did this example problem now where we can figure out the concentration of excess electrons, which are shown in the blue circles, and the excess holes, which are shown in the white circles. Okay, and the blue circle and white circles are near each other because they're created in pairs. Okay, the difference now is now we're going to turn the light off. Okay, so we turn the light off at t equals 0. What do you think is going to happen?
Recombination.
Exactly. So we turned on the light source. We generated these excess carriers, but then we turn off the light. And we have these excess carriers. As Melvin said, these carriers have a lifetime, right? I mentioned every generation process, whenever we create an electron hole pair, they don't last very long. And the typical carrier lifetimes, as you saw in an example problem, was like on the order of microseconds. So of course, these excess carrier concentrations, it's going to decay to 0. It's going to go away over time. So we can physically picture it as like, as when the light is turned off, the concentration of excess carriers decays exponentially with time, it turns out. Okay. So you can picture a lot of them disappearing at the beginning. And then as time goes, the rate of decay slows down a little bit. So I'll show you that again. So initially, there's a lot of excess carriers. A lot of excess carriers means that these electrons and holes are more likely to bump into each other. So at the beginning, the rate of recombination is high. A lot of them disappear. Then over time, as there's fewer and fewer excess carriers, the rate of recombination decreases. Okay, so if we were to plot this out in time, it would look something like this. It's an exponential decay. Okay, this is a very common thing in engineering. You guys know exponential decays are very common. Whenever you have a situation where the rate of something, the rate of a process depends on the concentration of something, you end up having exponential decays. Okay, a great example is in chemistry. In chemistry, has any of you studied Michaelis-Menten rate kinetics? Maybe you remember that. If not, no problem. But that's also, it shows that the rate of reaction depends on the concentration of the products that you have, or the concentration of the reactants that you have. Okay, don't worry about the details of that. I just say this exponential type thing is very common in engineering, chemistry, science, what have you. So the excess carrier concentration looks like this. And I'm just drawing sigma n as an example here, but you can imagine the same thing would apply to sigma p. So where does it start off with? The excess concentration starts off at sigma n0. That's what we calculated as a steady state excess carrier concentration, sigma n0. You can calculate that already. And then now you can see that it's just going to start off at that, but then it's going to decay to 0 over time, meaning all the excess carriers are going to disappear over time. And it's an exponential decay. It's given by this equation. So sigma n is equal to a function of time. So if, for people who like to have it written out explicitly, this would be sigma n of t is equal to sigma n0 e to the negative t over tau. And tau is the carrier lifetime for electrons. So we could say it's tau sub n. Here, let's add that into your notes there. Okay, so this tau sub n tells us the rate of decay. So for example, here's one example, the dotted line here. This is what, well, you tell me. We have these two dotted lines here, okay? Well, let's start off with this one. The dotted line here, does this have a larger or smaller tau sub n compared to the non-dotted line, the straight line? The solid line, I should say. So that's the question for the class. Comparing the solid line and the dotted line, which one has a larger carrier lifetime?
dotted one is the faster decay.
Right?
So it's a
Absolutely. Yep.
smaller tau.
You got it. You got it. Perfect. Yep. So as Janan said, the dotted line has a faster decay. Okay, faster decay means things are recombining faster. Faster recombination means the carrier lifetime is smaller. Okay, so small carrier lifetimes will have a quick, rapid rate of decay. And then a larger carrier lifetime will have a slower rate of decay. So if we compare these three lines here, this would be in order of increasing tau. All right. So bottom line here is if you illuminate the material, you generate excess carriers, you turn the light off, you will see an exponential decay in the excess carrier concentration. And it's just this basic inverse exponential function that we often see in engineering and science. So, if we were to derive a relationship for what the carrier lifetime is, and here's how we could do it. So, this number here, this carrier lifetime, can we actually derive a relationship for that from some physical principles? That's what this slide is about. Okay. So we ask the question, suppose we create electron hole pairs at time equals 0 with a short flash of light. So we generate the excess carriers. And then what is the resulting carrier concentration as a function of time? So this is kind of a derivation from what's going on in the previous slide. So we define sigma n of t as the number of excess carriers at time t. We can define a rate of change in the excess carriers. So we're going to a differential equation. The rate of change in the electron concentration is equal to the generation rate minus the recombination rate. So think about that for a second. I want you to see the intuition behind that. Generation rate is how quickly the electrons are being generated. Recombination rate is how quickly the electrons are going away, disappearing. So generation creates electrons, recombination removes electrons. So the generation rate minus the recombination rate is going to be your rate of change of electron concentration. The units for this, generation rate is I'll just write down the units here. It's 1 over centimeters cubed per second. It's a change in concentration with respect to time. Okay, for all three elements of this equation, it's 1 over centimeter cubed per second. Okay, so now we put in our equation for the generation rate. Now, before we found a relationship, when we talked about the generation rate, we said that the generation rate is equal to alpha r Ni squared. This was for the steady state case, but it turns out, and we're not going to talk about the details of this, but it turns out that this is also reasonable to use in this equation for even the non-steady state case, okay? A little bit of a blank I'm going to leave there, so we're not going to go into the details of that. Next is the recombination rate. Recombination rate is an equation that we're going to look at here that's probably new to you, okay? But it is equal to alpha r, which is that a recombination sort of a rate constant, and n0 plus sigma n, p0 plus sigma p. Now, I want you to see the intuition behind this. All this is saying is that the more electron concentration we have, the more hole concentration we have, that is going to increase the recombination rate. Let me just go back to the slide just to hammer this point in a little bit. We talked about generation and recombination at equilibrium here. Okay, and we said the generation rate is equal to the recombination rate, and these are both equal to the recombination rate constant alpha r times n0 times p0. Okay, and in steady state equilibrium, this NP is equal to NI squared. So this N0 P0 just became alpha R NI squared here. Okay. Now, what was our intuition behind this? I want to remind everyone that the more electrons you have, the more holes you have, the more likely they are to bump into each other and recombine. Whenever an electron sees a hole, there's a likelihood that it'll recombine. So obviously, the more electrons, the more holes you have, the larger your recombination rate is going to be. Okay, so at equilibrium, NP equals Ni squared. In non-equilibrium situations, which is what we're looking at right now, for the recombination rate, we notice we're plugging in the electron concentration and the hole concentration, just like we were before. But it's not just N0 and P0 now. It is N0 plus sigma N and P0 plus sigma P. Why? Because we're shining light on the material, so we created excess electrons and we created excess holes. So the electron concentration is now N0 plus sigma N. The hole concentration is P0 plus sigma P. So the fact that we have these excess carriers is going to increase the recombination rate. Okay, the generation rate is still the same as the steady state generation, but the recombination rate is dependent on the excess carrier concentration here. Okay, all right, so then now we have our differential equation, then we solve it. Now, solving it is not the focus of this class, it's not a math class, but you can solve this differential equation making some important assumptions that you're in an extrinsic material, meaning like you're in a doped material, it's either P-type or N-type, and you're also assuming low-level injection. Low-level injection is it's equivalent to what I said is the minority injection, okay? Both terms, for the purpose of this class, you can use it interchangeably. Most of the other books actually use low-level injection, so that might be, just remember that. So assuming low-level injection, what that means is that the excess concentration is much less than the majority carrier concentration. So in the case of electrons, the excess electron concentration is much less than N0. Okay, so if you solve this differential equation under these assumptions, then you will find that the carrier lifetime is given by this equation here, which I showed you on the last slide, and this tau sub n is equal to 1 over alpha r N0 plus P0. Okay. So the carrier lifetime actually depends on the electron and hole concentration. It's inversely proportional, as you might expect. The larger N0, the more electrons and holes you have, the smaller the carrier lifetime. Okay, so that all just came out of solving this differential equation. This is a good equation to remember in your head. Like, so what determines the carrier lifetime? This is what determines it. Okay, so I'm just going to show you a typical example of how majority and minority carrier concentrations change due to an instantaneous pulse. So in this example is gallium arsenide, by the way. It's not silicon like we usually do, just so you can see that this effect happens in different materials. So suppose we have a P-type gallium arsenide material. So the gallium arsenide actually has an intrinsic carrier concentration of 10 to the 6th per centimeter cubed. A lot smaller than silicon. Silicon is 1.5 times 10 to the 10. So 10 to the 6th per centimeter cubed, and it's doped with holes at a concentration 10 to the 15th acceptors per centimeter cubed. So the first thing we do here is we find out the concentration of electrons. A P-type means that your hole concentration is 10 to the 15th. Electron concentration can be found with NP equals Ni squared. And you come up with the electron concentration is 10 to the negative 3 per centimeter cubed. Okay, notice that for, with gallium arsenide, which has such a small intrinsic carrier concentration, you can end up having very, very low electron concentrations or hole concentrations in the material. In this case, 10 to the -3 per centimeter cubed. That means in every thousand cubic centimeters, you'd expect to find one electron. Okay. So in this material, a pulse creates 10 to the 14th electron hole pairs per centimeter cubed at t equals 0. What is the electron and hole concentration versus time? Okay, so I'm going to write out a few things here. So our N0 is 10 to the -3 per centimeter cubed. P0 is 10 to the 15th per centimeter cubed. So sigma n at time equals 0 is equal to 10 to the 14th per centimeter cubed, and sigma p at time equals 0 is equal to 10 to the 14th per centimeter cubed. So the next step is just figuring out the electron and hole concentrations with respect to time. So we can say sigma n of t is equal to sigma n0 e to the -t over tau sub n. And so this would be equal to 10 to the 14th e to the -t over tau sub n. The hole concentration, sigma p of t, equals sigma p0 e to the -t over tau sub p, 10 to the 14th e to the -t over tau sub p. So there's our equations for the electron concentration. And the last thing I want to just tell you is that the total electron concentration, N, is equal to, and N is going to be a function of time. It's going to be the amount before irradiation, N sub 0, plus sigma N of t. And then your hole concentration as a function of time is going to be equal to P sub 0 plus sigma P of t. All right, so I just threw up a whole bunch of equations on here. Hopefully you can make sense of it. But now we're graphing it on this plot here. So this is our P of t, and this is N of t. Okay, the thing I want you to just sort of observe on this plot is how different the N of t and P of t are. So let's look at some details of the plot. This is time on the x-axis, and the y-axis is carrier concentration. Notice this is on a log scale, 10 to the 13, 10 to the 14, 10 to the 15th. Now, if we were to draw, let's say, the electron concentration versus time, an inverse exponential function looks like this on a linear plot. But in a log plot, exponentials look like straight lines. Okay. So remember, if you take the reason why that is let's say, you have sigma n of t equals sigma n0 e to the -t over tau. If we take the log of it, then we get the log of sigma n0 plus the log of e to the negative t over tau. Okay, and the log of an exponential, so this ends up coming out to the log of sigma n0 plus, when you take the log of an exponential, you end up just getting whatever's in the exponential. So you end up getting negative t over tau. All right, so why am I mentioning this? It's a concept that many of you probably already know as graduate students. In a log plot, an exponential function looks like a straight line. And that's the reason why log plots are used in situations like this, because now you get nice straight lines to work with, okay? So what you can see with the electron concentration is that the electron concentration starts at 10 to the 14th, okay? 10 to the 14th e to the negative t over tau. So it starts at 10 to the 14th, and then it goes, basically, it goes down exponentially over time. Okay, so your n of t looks like a straight line like this. So this is plotting n of t, which is n sub 0 plus sigma n of t. So in the case of electrons, this sigma n of t, this is an important point. Sigma n of t is much larger than n sub 0. Okay, I'll say that again. Sigma n of t, in this case, is much larger than n sub 0. So your n of t basically looks like an exponential decay like this, because sigma n of t is an exponential decay. In the case of p of t, however, if you look at this line up here, in the case of p of t, this term is bigger. P sub 0 is greater than sigma p of t. All right, this is a case of low-level injection. Low-level injection means the minority carrier concentration, which in this case is the electrons, changes very significantly when you shine light on the material. But the majority carrier concentration, which is the holes in this case, only changes by a small amount. So the excess carrier concentration is much relatively insignificant compared to the well, let me rephrase that. The excess hole concentration is not that much larger than the original hole concentration. So what you end up with is a plot that looks like this instead. So it's a little bit increased at the beginning. It's a little bit larger at the beginning. At the beginning, it's 10 to the 14th. Sigma p is 10 to the 14th. P0 is 10 to the 15th. So you end up getting 1.1 times 10 to the 15th, and then it decays down to 10 to the 15th. Okay, P0 is equal to 10 to the 15th. This term becomes insignificant compared to this one. All right, so you can see the majority carrier concentration decreases by orders of magnitude over time. I'm sorry, the minority carrier concentration decreases by orders of magnitude over time. The majority carrier concentration here, it basically flattens out at close to 10 to the 15th. Okay, so again, telling us is that there's a lot of interesting things happening with the minority carriers. All right. Looks like we're not going to get to carrier diffusion today. That's too bad. Okay. So let's just talk about photoconductors and applications of photoconductors. Just kind of a fun thing for the last few minutes of this class. So photoconductors are materials that change resistance when illuminated with light. I don't know if any of you are familiar with this electrical symbol, but this is a symbol for a photoconductor. So what it's showing here is showing a resistor. So you have a certain resistance here. And then the fact that you have a circle around it with two arrows here means that when this resistor is illuminated with light, the resistance changes. Okay, and now we have enough information in this class. You know enough about semiconductors to know that semiconductors can be used to implement photoconductors. Why do we know that? Well, semiconductors, when they're irradiated with light, You radiate with light. As long as that light energy is greater than the band gap, you create electron hole pairs. If you create electron hole pairs, then the material becomes more conductive because you have more carriers, you have more electrons and more holes. Okay. Just reiterating the point, in order for you to generate electron hole pairs, the energy of the light has to be greater than the band gap. So photoconductors have applications in laser printers, security systems, night lights, things like that. Any place where you need to detect light. And I'm giving you this equation for the conductivity of a photoconductor. You'll have an example problem in your homework on this. I'm just going to put the original formula. The original formula for conductivity of a semiconductor looks like this. Sigma is equal to Q mu n times n plus Q mu p times p. And then if you collect the Q terms together, it'll look like this. So this is the basic formula for the conductivity of a semiconductor. So when we shine light on the semiconductor, we're just creating extra electrons and we're creating extra holes. So all that's happening here is that this N, the electron concentration, is now becoming N0 plus sigma N. This N is becoming N0 plus sigma N. This P is now becoming P0 plus sigma P. Right? And the sigma N and sigma P, we've looked at the equations for that before. If you're doing steady state illumination, then sigma N and sigma P are given by these equations shown. So basically, shine light on the material, electron and hole concentration goes up, so the conductivity also goes up. So just some quick examples of photoconductors. How many of you have seen Ocean's 11? The movie. Corey has. Let's see if I can do a little YouTube search on it. There we go. I don't know if I'll get in trouble for showing a video and copyrighted video in class, but oh, this is Ocean's 12, laser fields. So you can't hear the music. The music makes it a lot more entertaining, but you know, in Hollywood, they always show security systems which are based on laser lights. And you know, the the thief has to deftly avoid those laser systems to avoid tripping the laser or tripping the security system. So I really like this scene. But how does a photoconductor system work? How does this laser security system work in practice? It actually involves photoconductors. So all this is suppose you have a laser. So laser's going this way, and then here you have a photoconductor, and the photoconductor is part of a readout circuit. So the photoconductor has a certain resistance associated with it. So the laser is hitting the photoconductor, and when it's hitting the photoconductor, the resistance is at a certain value. Okay, so now imagine that some person gets in the way and blocks the laser light. What's going to happen to the resistance? Last question of the day. The photoconductor has a certain resistance when the laser is shining on it, and now the thief gets in the way and blocks the laser. So now there's less light going to the photoconductor. What's going to happen to the resistance?
Will it spike?
It'll spike.
Will it?
Exactly.
Oh, okay.
It spikes because, the more, when when the laser light was shining on the material, you had a lot of excess carriers from the laser light.
Okay.
Now the laser light's taken away. You don't have as many carriers. You don't have as many electrons and holes in the semiconductor. So the conductivity of the semiconductor goes down. Conductivity going down means the resistance. The resistor value goes up. And so you can design circuits to be very sensitive to changes in resistance. And so that's basically how these old laser-based security systems work. And nowadays we have better ways of doing it with like cameras and machine learning and stuff like that. But it's kind of fun, I always love these like Hollywood movies where they're showing these old types of systems. Same type of thing is used in exposure meters and cameras. So if you have a camera and you want to, in photography, you want to know how much light is coming into the system so that you can determine your shutter time. So it's used in exposure meters. They're also used in basic night lights. When it gets dark in the room, the light turns on automatically. Okay, so those are some examples of photoconductors. We'll get into diffusion next time in class. So today we talked about steady state and transient behavior of optically induced carriers. All right, thanks everyone. So if there's any questions you have between now and Monday for the exam, please let me know. If there's additional office hours anyone would like to do, please let me know that as well. We can certainly do that. Okay, so good luck studying for the test, and I will see you all on Monday.
All right. Thank you.
All right, have a good one.